Problem number 8 asks us, a room has 8 light switches, each of which controls a different light. All right, so let's draw that out really quickly. Here's the room. And 1, 2, 3, 4, 5, 6, 7, 8 light switches. All right? So, let's keep reading. Initially, exactly 5 of the lights are on. All right, so let's draw that out. 1, 2, 3, 4, 5 are on. Okay? 3 people enter the room, one after another. Each person independently flips one switch at random and then exits the room. All right, so let's draw it. The remaining 3 are off. All right? So, let's keep reading from there. What is the probability that after the 3rd person has exited the room, exactly 6 of the lights are on? Okay, so we know that if we want 6 of the lights to be on at the end, and we have 5 on right now, that 2 of the 3 people have to turn lights on, and the remaining 3rd person has to turn a light off. Okay, so let's write that out. The first person turns on, second person turns on, and the 3rd person turns off with F for off and O for on. Okay, so let's say how many different arrangements are there of this these 3 people? Well, there are 3. There's OOF, OFO, and finally FOO. From there, what we want to do is we want to find the probability of, or the amount of ways that these could happen. So let's just really quickly, let's move this diagram off to the side really quick. Okay. Grady. There we go. Alright, that's the best we're going to get, I think. Alright, so we have the diagram over there. We don't really need that from this point on. Alright, so let's start off with this first arrangement, OOF, and let's see how many ways we can make that one. Well, if the first person is going to turn a light that was not previously on, that means that they have to turn one of the 3 lights that was off on. So to start off with that one, we'll get 3 options for the first person. The second person, there are only going to be 2 more lights that are still off that they can turn on. So let's multiply that by 2. And then the 3rd person turning off, well, there's a total of 7 lights that they could turn off that are already on. So let's multiply that by 7. And we multiply those 3 numbers out, and we get, what is that? 7 times 2 is 14, times 3 is 42, I believe. So we get 42 after multiplying those 3 out. The next arrangement, OFO, to do that one, we're going to start out with this O. Well, just like the one above it, we know there are 3 options because there are 3 lights that are off at the beginning. The second person turning a light off, all right, there are going to be 6 lights that are on that they can turn off. So let's multiply that by 6. And then this 3rd person coming back into the room to turn a light on, there are going to be 3 total options for them to turn on that are off. So we multiply those out and we get 54. This third arrangement, FOO, starting at the beginning, the first person is going to have 5 lights that are already on that they can turn off. The second person coming into the room will have 4 lights that are off that they can turn on. And then the 3rd person will have 3 lights that are off that they can turn on. So multiplying those all together, we get 60 possible ways for that to happen. So now we can add all of these numbers together. And when we add all of them together, we're going to get 156. Okay? So let's write that out as 156 ways that there could be 6 lights on after 3 people have come in. Well, how many possible ways for 3 people to come in and turn off and on the lights are there? Well, we know there are 8 choices, and there are 3 people. So 8 times 8 times 8 is equal to 512, I believe. Yes. So that means that there are 156 ways for there to be 6 lights on at the end out of 512 total ways for the people to come in and turn on and off the lights. From there, we just have to simplify that, and we can simplify that down to 39 out of 128. So that 39 of 128 is our answer.